What is the specific problem that the proposed method aims to solve in the context of learning from preference feedback?
The specific problem that the proposed method aims to solve in the context of learning from preference feedback is to systematically investigate key components of learning from preferences to understand their impact on downstream model performance. The study aims to explore the effects of varying preference data, learning algorithms, specifically comparing PPO and DPO, reward models, and policy training prompts on the performance of language models trained with preference-based learning. The goal is to determine which aspects of learning from preferences are most crucial for improving model performance across various capabilities, such as reasoning, coding, safety, truthfulness, instruction following, and factuality. The study seeks to provide insights into the importance of different components in preference-based learning to guide the development of more effective training strategies for language models.
How does the proposed method work, and can you illustrate it step by step?
The proposed method works by systematically investigating key components of learning from preference feedback to improve downstream model performance. The method starts with an initial strong open supervised fine-tuning (SFT) model and explores various aspects such as preference data, learning algorithm, PPO versus DPO, reward models, and policy training prompts. Firstly, synthetic preference datasets with per-aspect annotations are found to perform best, especially in truthfulness. Secondly, PPO is shown to outperform DPO in reasoning, coding, and safety capabilities, while truthfulness tends to degrade. PPO-trained models exhibit improved chain-of-thought reasoning abilities and perform better at tasks like alpaca-val. Thirdly, improving reward models through scaling up training data and reward model size does not necessarily translate to significant improvements in downstream performance. Lastly, using targeted prompts, especially those closely matching the test settings, can lead to significant improvements in specific capabilities like math performance. However, altering prompts to focus more on specific tasks like math and coding may not always improve overall performance, as seen in the results presented in the study.
What are the theoretical or practical benefits of using the PPO algorithm compared to the DPO algorithm in learning from preferences?
The theoretical and practical benefits of using the PPO algorithm compared to the DPO algorithm in learning from preferences include improved reasoning, coding, and safety capabilities. Specifically, PPO outperforms DPO by an average of 2.9, and 2.3 points for reasoning, coding, and safety, respectively. Additionally, PPO-trained models are more likely to excel in chain-of-thought reasoning, even without in-context examples, suggesting enhanced reasoning abilities. While truthfulness may slightly degrade with PPO, instruction-following abilities remain largely similar, with PPO models performing better on specific tasks like alpaca-val 1 and 2. Overall, PPO demonstrates superior performance in various capabilities, making it a more effective algorithm for learning from preferences compared to DPO.
How were the reward models studied and tested in the experiment?
The reward models in the experiment were studied and tested by first considering two ways to improve a reward model: scaling up the training data for the reward model and scaling up the reward model size. The study involved constructing a data mixture of the top-performing datasets and training reward models at two scales of 13B and 70B starting from Tulu 2. The improved reward models were then tested to see if they lead to enhanced downstream policy models when used during PPO training. The experiment involved performing PPO training using the ultra-feedback prompts during training and evaluating the results. Surprisingly, the findings showed that improvements in reward models resulted in marginal to no improvements in overall downstream performance. The study revealed that while there were small improvements in overall performance from using the larger 70B ultra-feedback RM, the improvement was largely driven by a significant performance jump in GSM, while other metrics remained largely similar. The experiment highlighted the difficulty in translating improvements in reward models to the underlying policy and emphasized the importance of evaluating over a diverse set of test tasks to understand the impact of reward models on downstream performance.
What were the key findings related to the downstream model performance when comparing DPO and PPO algorithms?
The key findings related to the downstream model performance when comparing DPO and PPO algorithms are as follows. 1. PPO outperforms DPO across varied datasets, particularly improving reasoning, coding, and safety capabilities the most. 2. On average, PPO models showed an improvement of 2.9 and 3 points in reasoning, coding, and safety respectively, while truthfulness tended to degrade by an average of 5.3. PPO-trained models were more likely to perform chain-of-thought reasoning, even without in-context examples suggesting enhanced chain-of-thought abilities. 4. While instruction-following ability remained similar between PPO and DPO models, PPO-trained models performed better at AlpacaVal 1 and 2 with an average improvement of 3.4 points on AlpacaVal 2 compared to DPO-trained models. In summary, the comparison between DPO and PPO algorithms revealed that PPO generally leads to improved downstream model performance, particularly in reasoning, coding, and safety capabilities, showcasing its effectiveness over DPO in various evaluation settings.
What are the implications of the results obtained with the policy training prompts on the overall performance of the models?
The implications of the results obtained with the policy training prompts on the overall performance of the models suggest that using targeted prompt distributions can significantly improve performance when coupled with powerful reward models, such as using prompts closely matching the test settings. Specifically, when prompts are aligned with the task at hand, like in the case of math capabilities as evaluated by GSM, models trained with larger reward models show significant improvements in performance. However, weaker reward models struggle to leverage prompts that differ from those they were trained on, leading to poorer performance. Additionally, the study found that altering prompt distributions to focus more on specific tasks, such as math and coding, did not consistently improve overall performance in the generalist setting. This indicates that the diversity of prompts in the original dataset, like ultrafeedback, already allows for strong performance across various tasks, and shifting the prompt distribution away from this diversity can actually hinder overall model performance.